We are in the home stretch of Intro to Functions. This is a long section, and you're just going to have to hang in there. Hopefully, many of you are starting to see the patterns with these domains, and it will become a little more doable as we go along. Our first function here that we need to identify the domain on is g of x equals x over 4x squared minus 9. Notice that the denominator could be factored, and so we'll go ahead and do that. 4x squared minus 9 would factor to 2x plus 3 times 2x minus 3, which does help us identify where our vertical asymptotes would be. If I set 2x plus 3 equal to 0 and solve for x, I'll have 2x equals negative 3 and x equals negative 3 halves. If I set 2x minus 3 equal to 0, I'm going to get x equals 3 halves. When I plug or substitute in negative 3 halves and 3 halves into my g of x, I will get undefined results. You can check this in your calculator as well, and it doesn't work. You have a big problem with your domain. Some calculators will even say domain error, which is helpful. And so I'm just going to go ahead and draw a number line, label my negative and positive infinity regions or directions, and I'm going to put an open dot at negative 3 halves and an open dot at positive 3 halves. Notice there are no even roots in the numerator or the denominator of this fraction, and so the only restrictions on my domain are where the function equals negative 3 halves and positive 3 halves, okay? So we will throw out just those exact values. They're infinitely small, but for the purposes of visualization, I've drawn them to be these giant open dots on the number line. So we're going to write open parenthesis, negative infinity to negative 3 halves, close parenthesis, union, negative 3 halves to positive 3 halves, union, 3 halves to infinity. That is my domain. We have f of x equals 6x minus the square root of 5x minus 6. Notice that in this example, we do not have fractions, but we do have a radical. To find the domain for radicals without just an x underneath, because we know they can't be less than 0, we actually have to set up an inequality where the radicand, I like to call it the guts of the radical, but the radicand is greater than or equal to 0. Because remember, a 0 in a radical can exist as long as it's not in your denominator. And in this case, the radical is not in the denominator, and so that is not a problem. If I find the value for x that is true for this inequality, I subtract 6 from both sides, then I divide by 5 on both sides, and x must be greater than or equal to 6/5. There are no restrictions on the first term of this function because 6x has no radical and it has no fraction. If I wanted to draw where this inequality is true, again, you don't have to do this. If you know what this inequality converts to as an interval, you don't need to draw this graph. But let's just for visualization purposes, there's the dot, 6/5. Notice that if you solve an inequality and you get x on the left, your inequality will always point in the direction your arrow will go, or the area or region that the inequality is true, which is so cool. I remember when I first realized that it was... Okay, so my interval is from open bracket 6/5 to positive infinity, close parenthesis. Remember, for infinity, it's always paired with a parenthesis. You will never reach infinity, so you put a parenthesis there. So my domain for this region that is true is anything from 6/5 to positive infinity. Now let's take a look at example F. We have h of x equals the 6th root of 4 minus 2x. Remember, we check two things. We check, does the function have a fraction in it? In this case, no. And does the function have an even root in it? And in this case, it does. The even root is the 6th root of 4 minus 2x. That means that the radicand, or the guts of the radical, has to be greater than or equal to 0. Then solving this inequality for x, I'll subtract 4 from both sides. Divide by -2 on both sides. And x will be less than or equal to 2. Notice that when I divide or multiply by a negative number, I have to remember to flip my inequality over. Drawing a number line from -infinity to positive infinity, putting a closed dot at 2, and drawing the interval on which the domain exists for h of x. My domain will be from -infinity, so open parenthesis, -infinity, comma, to close bracket. Let's look at example G. We have p of x equals 2 square root of x squared minus 8x plus 15. Now, I know that the parabola that is represented underneath this radical is an upward pointing or upward opening parabola. So I know the only region on which this can exist is where it is positive or equal to 0 as a parabola. Let's see if I can factor this quadratic. I have an x and an x for my binomial. I need a -3 and a -5 to get positive 15. And those two negatives will add to a -8, which means that my roots on the polynomial or parabola will be at 3 and 5. Since it's an upward opening parabola, I know that anything between 3 and 5 will be negative. So I must throw out the interval between 3 and 5. That means the only interval for which this function can exist is less than 3, or when less than or equal 3, there we go, or x is greater than or equal to 5. And I was able to identify that simply by sketching the graph of the polynomial or parabola. It would be a very good idea to remind yourself how to find the roots of a polynomial, because that will really help you with where the region is positive and negative. So I'm going to sketch a number line. We'll include the point at 3, will include the point at 5. Anything to the left of 3 is included. Anything to the right of 5 is included. And we throw out the interval that is negative between 3 and 5. So my domain for this function will be between negative infinity, so open parenthesis, negative infinity to 3, close bracket, union, open bracket 5, comma, infinity, close parenthesis.